So our next question looks at these honor text. Chapter 1, practice problem 27. And it states, use figure 1 tac 16 to determine the mass required to stretch the spring 15 centimeters. So of course first you got to figure out, hey, what's figure 116? Those refer to figures within your book, like this one. It's called figure 1 tac 16. It's great. Alright, cool. So this is the one they're talking about, and let's see, you'll find this on page 16, looks like. Alright, so here's our relationship of mass versus length. Your x-axis, of course, is your independent variable. Your vertical axis, or the y-axis, is your dependent variable. Let's refresh what the question is here. Determine the mass required to stretch the spring 15 centimeters. And they have a nice line here drawn for you. So looking yourself along with that graph, I'm going to look at the side because I have to write for you now. I see that, well, they have B, or the y-axis, in a line slope intercept format. Remember, that's y equals mx plus b. Slope intercept form. Forget these terms after a while. Good thing to keep coming back though. So they have a b mentioned, and they tell you in red that b is equal to 13.7. Now you should know, what does b match up to? Well, that's the y-intercept. So if it's the y-intercept right here, then that corresponds to a 0 value on my x scale. So when x is 0, y has a value of 13.7. So there's no mass on it. How far is that spring stretching? It's not. Okay, remember, you still got to think in science concepts, what's actually going on here. So it's not stretched, or you could say your stretch value is equal to 0. Now remember, we're looking for a stretch value of 15. So the total measurement of the spring is being suspended with some mass underneath it. When there's no stretch, right, here's what we're saying. When there's no stretch, b equals 13.7. You could say for xy coordinates, this would be 0 mass and 13.7 centimeters. Because with no mass placed on it, that is the length, the full length of the string, the spring, which is not yet stretched. So I want to add another 15 centimeters on that, right? So I would like a, I would like a y value of 13.7, which is what it already is relaxed, and I would like to stretch 15 more centimeters. So I'm looking for a y value of, let's see, 13.7 plus 15, that's 28.7 centimeters. Alright, that's our y value is going to be, but we need to take a closer look at our slope intercept form so that we can complete the other unknowns in that. So looking at y mx plus b, I know what my y wants to be. I already know what b is. That value is set because the characteristics of a line, that's a unique intersection there, only on the y-intercept. That value is set. It's set to determine the mass required. Well, that's my x value. This is what I'm looking for. I know what I want this to be. I know what this has to be. That's what I'm looking for. I still have an unknown here because I'm not really sure what the slope, or m, is yet. But it looks like with a little bit of examination on our graph, we could figure that out. So let's take a look at slope again on our display, and I'll just bring it up. So I need to find out what the slope is, which is rise over run function. And let's see if they, no, they don't. Everything comes on the graph just like it is. So where could we find some good intercepts and maybe try to eyeball this? It looks like 16.0 centimeters will correspond with 13 grams of mass pretty closely. And it looks like right about here, which would be 14.5 centimeters, would correspond with 10 grams of mass. So I'm going to record those 2 points. So my first point, first set of coordinates, we'll call it x1, y1. Now that'll be the lower value one. So that intersection we had mass of 10 grams and a length of 14.5 centimeters, 14.5 centimeters, and x2, y2 to correspond with the other point. Easy to determine on our slope. So that was a 30 grams of mass and a length of 16.0 centimeters. Okay. So now I have these difference of 2 points, full values for those coordinates. We know that slope is equal to rise over run. So when we're talking about rise, we're talking about how much y changes, because our y is going up and down. That's our rise. So I'm looking at a change in y, run, that's how it runs across the graph. That's the x-axis, as my value of x changes. If you haven't run into deltas yet, delta means simply change. Usually in our case a change in, or it could also mean a difference. So therefore, a change in y, we'll look at our final position where we end up at, and we'll take away where we started from, and that should tell us what the difference between them is. So I end up at 16 centimeters looking at this for slope considerations. And my original point was 14.5. So this is going to be y2 minus y1 over x2 minus x1. That's change in y position, the final one minus the initial one. And for x, change in its position, x2 over x1, I'm sorry, x2 minus x1. And this is all for the case of slope. So we can say that slope, which of course was our m value that we were looking for earlier, and slide that in up here. y2, which was 16.0 centimeters, minus y1, the first y coordinate, which is 14.5 centimeters, and on the denominator, x2 is 30 grams minus original X position, which was 10 grams. So hit this out. On the top, what do I end up with? 16 minus 14.5, that's going to leave me 1.5 centimeters divided by 30 grams minus 10 grams equals, you got it, 20 grams. That's what our slope is. Of course, you might want to make that into a I'm not a fraction, but a completed out decimal here. So let's figure out 1.5 divided by 20 is 1.5 divided by 20. So slope equals, only have two sig figs in there, slide 1, slide 2. Much easier to work with it this way when we're working in physics. I'm gonna keep it like this if we can. That's our number resolved, 1.5 divided by 20, and centimeters divided by grams. That's length, that's mass. So I can't divide them out or simplify them, so I just carry them with me. Okay, so this here is the value for slope. All right, so now what does that tell us? Well, going back to our original question, determine the mass required to stretch the spring. Well, we had to find out what the relationship with it between mass and the length of the spring, how the length corresponds to the actual stretch of the spring. Where we started at the y-intercept. Ugh, been a great day. Y-intercept, and y is what it is. So now we can just take this and we'll say, okay, y equals, oh, let me slide it up some. Y equals mx plus b. I know what I want this value to be because they tell us 15 centimeters total length. Right, and we determine that's the original non-stretch length plus how much we want to stretch by the 15. So I know what the y value is going to be. I just determined what the slope is. I know what that is. B was initially given to me. All right. So this is what oh wait. Yeah, that's right. I know this one. I'm looking for this x value. This is what I do not know. So I need to rearrange this as an expression of x. Y equals mx plus b, so I'm going to subtract the b over. Y minus b equals m times x. I want x by itself, so I'm going to divide both sides by m. I gotta do it to the whole side, not just one part of it. So this becomes y minus b, the whole side divided by m. And that will leave me simply with x on the side. So I now have a pure expression just for x, which is the stretch of the spring so now I should be able to substitute and solve for this. So y minus b, what is y? Where do we determine y at? Oh, that's our final position. We did a little bit of earlier footwork on that. We want it finally to be in the position of 28.7, which is where it starts at 13 plus the amount we stretch. So 28.7 centimeters for y, minus b, which is the length it was with zero mass on it. 13.7 centimeters. All divided by m, which is our slope, which we determined right up here, right here. So m goes on the bottom, 0.075 centimeters per gram. All right. Well, let's figure out these numbers first. So x will equal 28.7 minus 13.7 centimeters. That's 15 centimeters over 0.075 centimeters per gram. All right, well, we could say, well, let's simplify that one more time, because it's just we only need one set of digits, not two of them. So 15 centimeters divided by 0.075 centimeters per gram. The number is going to be 200. 200. Now we still have centimeter units on top, cm, and centimeter per gram on the bottom. Centimeters divided by a centimeter, that will cancel. So now I essentially have 200, and my units will be a 1 and 1, will be a 1 over g, which is just the inverse of 1 over g, which is the inverse of g. So if I take the inverse of an inverse, what I end up with? 200 grams. Box it off so Mr. Thompson can find it, and you are done.